All right, so back into the coding session, and we're on a new setup now. You might notice things look a little bit different. We're on Omachi now on my new framework laptop. Omachi is a derivative of Arch, by the way. The other little thing that I changed was Omachi has a built-in screen record feature, and I have this little window which I can actually see while I'm recording. Previously it was just added by OBS, but it's kind of nice to be able to see it so I know if I'm sitting in front of something. But having changed to Arch, and I think we have a newer version of NASM and all sorts of things. I've kept the same version of Odin because when I got the latest there were just a whole bunch of breaking changes and I couldn't be bothered fixing those up. But without further ado, let's keep going, because I also left us with a bit of a cliffhanger in the last session. Just making sure my door's shut. I don't want to sound weird to my flatmates. Yeah, last session we came across an issue when we were running OpenGL. These are the issues that come up when we switch. When we switch to a new operating system. It's a good test actually, but I think this one here is to do with, I think it's a newer version of NASM, because now it's complaining about this. But I've looked this up already, and if I go to program generation and the first line of the program, if we say default to relative. I think it means relative addressing instead of absolute, something like that. If we run that, that should get rid of that warning. And then we have this problem, which is actually in main. It's here. So this is when we do LD to link. We need access to the dynamic linker, which is in a different folder. So I'm just going to correct the path now. I want to detect the correct location of this file eventually. There is a way to do that, but can't be bothered doing it in this session. So we're going to leave it for now. Yeah, so that should fix that. We should be able to run OpenGL now. And there we go. And we have our issue. So it's I'm also using a tiled window manager, so it looks a little bit weird now because it takes up half the screen. But it's still fine. We can still see the triangles. It's fine. So we got that panic index out of bounds. That was the cliffhanger issue. What I discovered was, because in assembly we have a limited number of registers, I think the highest number in x86-64. I think there are extensions where you can get more, but I don't think it has a lot of support yet. So the highest we have is number 15. So we have to be careful not to use too many of these registers and overflow. We don't actually have a mechanism for overflow right now. I think the idea is that you should overflow into the stack. Just start using stack space if you don't have any more registers to use. But that sounds complicated. So let's not worry about that right now. What we will worry about is the fact that I guess we were being a little too careful not to use too many registers, and we ended up reusing a register before we should have, which meant that some data got overridden, and then we tried to use that overridden data later, and it does not work. So the data that gets overridden is this length, which is mostly used for bounds checking, I think. We use it for bounds checking here because we're, just to recap, this is what we changed in the last session. What did we change? Was it this? You know, I can't actually remember what we did in the last session. It's been a little while. I just remember that it had this issue, and this is to do with arrays. So we're getting the length of the array or slice. That's what getLength does. It gets the location where the length is stored for the array or slice. For the array, it's actually an immediate. It's stored in the AST, so we just make an immediate. And we actually have a memory address for slices. Anyway, that's not really too important. I think what we do need to do, though, is we need to make sure that we copy this into a register, because right now it might use a register. No, it's just immediate, or no. So this is the problem. It's because it's using an offset to a known address, the container location, and if that location gets changed, you know, now I can't remember exactly what the issue was, because that doesn't sound right. If this is a memory location, we're offsetting it. I think that's right. The memory location could be a stack address. And then if we do more allocations, like we do down here, then that stack address gets invalidated. I think that might have been what it was. So I think what we need to do anyway, I'm pretty sure I know, even though I'm forgetting all this stuff, I think what we do need to do is copy this guy to a register. So I think we need to pass in the context, the thing to copy in, the register number that we're copying to. So we're going to do +1. And then what else we need to pass in? The type node. So this is a length that we're dealing with here, so we can use the length type node. So now we know that that is in a register. So allocations can't mess with it. I don't know how this used to work actually, but now it doesn't. But now that it's in a register, we also need to be careful that we don't override that register. So I want to look at everywhere where we use register num. So already immediately here, we're using register num +1 to store the start expression location. So what I'm going to do is I'm just going to bump that up to 2. Because register num is kind of like our main register number for this expression, or this primary, you could say. So the primary itself generally sits in that register number, if it is in a register. It might not be, but if it is, then it uses that one. So that's kind of reserved. So now we use all these pluses to store additional data that we use when we're figuring out the primary. So for the start expression, we use +2. Here, see, we're not using a plus, but this is a fast path. This is actually returning data location. So it's kind of like this is the primary thing. So it makes sense to put it in here. And it doesn't matter that it's overriding, like at the moment, the child node of this subscript, because up here first we generate the child node. So we get the first child and we recurse for that, and we use register number for that. So this location could be in this register, but it doesn't matter to override that because this is what we actually want to return. While I'm here, actually, this is kind of messed up because this is trying to figure out, like, if it's not a slice, which means it's an array. So I don't know why I didn't just say is array, but let's not change that in case it breaks something. But so if it's but if we're looking at number literal, that means it's an array. I'm gonna say that. Hopefully it doesn't break anything. But previously, the first child of the node was the index, the number that we're indexing into the array with. No, the length of the array? No, yeah, the number that we're indexing into the array with. Oh, maybe that's why, because we're not changing something into a slice. Doesn't mean we're changing it into an array. That means that, go away. That means that we're indexing. We're not creating a slice, we're just indexing into an array or slice. Anyway, so if this is a number literal, that means that what I was trying to check was, oh, it looks like we have just used a hard-coded number to index into it. Do I have an example of that? Like this. We're indexing into an array, we just use a hard-coded number. In which case, at compile time, we can just say, okay, I know that it's a 5, and that's why we check for the number literal. Long way of explaining the fact that now these numbers, they are implicitly changed so that it goes like this. It gets wrapped in this conversion. See, in this case, it's a U. Well, in this case, doesn't have a type yet. So it gets cast to a U32, which means that the AST has this cast operation around it, which means, so I'm going to use start expression node, because start expression node in this case is node.children1, which is what we have here. But instead of just going node.children1, we need to go node.children1, which would be the first parameter of that conversion, the U64 call, no, U32 call, and then we get the first chart of that, which would be the number. Sorry, it's confusing, but so we also, in both places, we need to use this node. This node will be holding, long story short, this whole node will be holding the 5. So this is what we check for a number literal, and this is where we grab the 5. Oh my god, why does that keep getting pasted there? So anyway, let's keep going with this register number business. So now we get this address location, which is also being put into register num without a plus something. But address location is actually what we're going to return from here. If we go down to the bottom, see, that's what gets returned. So we're happy with that. That's okay. That's okay. That's good. It's a good thing that it should go into that register number. But then here, this offset location, we'll bump that up to 3 because 2 is already being used by the start expression. And then if we go a bit further down, there's some more here. And this here is the end expression, which is using +2. We're going to bump that up to +3 as well, which means it's using the same register as this, but this is only used oh my god, am I just like pasting stuff in all sorts of random locations? This offset location is only used in this little area here, so it's okay down here for us to reuse that +3. Where is that? Where is that code that reuses the +3? Here it is. And I think that's the last of it. Yeah. And then this is like returning. So this is the primary thing. So that's register num address location. So this ensures, all of this ensures that we are not reusing any registers, and also that the length has been copied, the length location has been copied into a register, so allocations don't affect it anymore. That's kind of the fix we've done. And the other little thing, in the last session, we played with this a bit. So we said left-hand side gets register num, right-hand side gets register num +2. We're going to revert that back to 1. And then if we look for all the instances of register num, actually if we look for register num plus something, here we go. So there are a few things here, just a couple, that use a plus. This is a length that we use. We need to compare with the length. So this Is this some bounds checking or? Oh no, I think this is just some comparison between slices. So we need to compare the lengths of the slices. Now this stuff I'm going to go +2. And I think there's some more down here. +2. Maybe I'll say like that. So this used to be +1, we're going to get +2. So that's our hint for when we look at, because this said more testing, so there was something wrong with it. And down here, there's just another place where we can do a +2. Well, this is the right hand side. So right hand side we can say +1. So right hand side stuff. So we see the right hand side is +1. And the other ones I make +2 because when they are in these kind of functions, and we don't want to override either of these while we're in here, right? So anything in here we should use +2 or higher because we've already used this one and +1. Confusing register stuff, I know, but fingers crossed that works. There, so it didn't crash that time. So I'm happy with that. Let's just check the playground looks good, and we'll do a health check. See if that works, and then we'll move on to the next thing. Okay, that works. So let me just do a whip commit. All right. So the next thing I want to take a look at is dynamically sized SOAs, structs of arrays. Oh my, is there some sort of shortcut thing that I'm accidentally pressing? I just keep doing it. Okay, so this guy here, structs of arrays. So if I do an example, if I make a struct type, which is like A, U8, B, U8, C, U8. So it's got 3 U8 members. And then we say our SOA is a hash SOA. The struct will give it 5. So it's an array of 5 SOAs. Well, it's an array of 5 the structs, but because we make it an SOA, we haven't worked with these for a while, but what it does is it basically takes it from, it changes it from being this, whoops, to being, oh my god, what am I doing today? What? How does that even happen? Okay, so instead of this, it becomes this. So all the members become their own array. You can think of it like that. So it's a struct of arrays, an SOA. And the reason you might want to do that is just for, it can make it more performant in some cases. You can make a big fat struct with lots of members. And there might be some batch operations you want to do on big lists of these structs. But they only care about A, or they only care about A and B. And that means that you only need to bring A, if it's only dealing with A, you only need to bring A into memory. You only need to read A. You only need to put that into the cache. You don't need to put the whole struct into the cache for every A, which can be very performant because getting stuff into the cache is very slow. And then I think at the moment, how we have to access it is like that. So that's how I would assign a 9 to somewhere in the struct of arrays. It would be nice if we could do that syntax. We used to be able to, but then I got rid of it. Oh, the health check was fine. So if I run the SOA now, so it doesn't complain, everything is fine. And under the hood, what happens is that it performs that conversion. So the AST gets changed so that these are all arrays. Okay. Now, the problem is what if we come along with oh, I like to do that format. What if we come along and we use that? So that's not valid for on the stack, but if we were to heap allocate, then we can have a dynamically sized array. It returns as a slice. This would, or normally, we'll get to that. Normally, like this here ints will actually be a slice of ints because it needs to store the pointer and the length, which is potentially not known. Well, the pointer is definitely not known at runtime. I mean at compile time, and the length may not be. Anyway, so this is what we want to be able to do, and this is not does not work yet. We get lots of errors. So let's see what we need to do to get that working. I think the first thing, I think we need to look at I believe it's the assignment. So we'll go for type checking assignment first. When we get to the memory allocator stuff, I think it's in here. So if it's an array, like I said, if this is an array, then we convert it to a slice. That's what we do here. If it's not, then we just convert it to a pointer. Just like if you do new, in another language, you get a pointer to it. So this is converting it to a pointer. So we need an extra little something. I think I'm going to make another helper function. So maybe like is SOA. And then we're going to do something different. So let's make that is SOA. Is SOA is saying that we have so the data type, so we don't, I think it would be like an identifier that we pass in. So the data type is a struct type. And the other thing that makes it an SOA is that I guess we don't need to do AST dot here, do we? We're in AST. So get modifier SOA does not equal nil. So it has that identifier, that modifier. So it's a struct with that modifier. That's how we know it's an SOA. Because when we get to here, we have already converted it. It's already been converted to that structure where it's a struct with arrays in it. So it has the struct type, but it still has the SOA modifier on it. So in here, I think what we need to do, we need to get the length. And this is converting to a slice. What we're actually going to do is we're going to convert all of the members to be slices. Because we still need to, just like we do with this array case here, we still need to have the length stored somewhere, and we still need to have a pointer for each member. So it makes sense to have a slice. And then the code can just handle it like it handles any slice. So that's nice also. So we need to, first let's see how we get the length. So the length will be, so the data type is the struct. And at the moment, if we go to left-hand side expression, this is where we actually do the conversion, isn't it? Somewhere. Oh, this is right-hand side. Left-hand side expression. Yeah, see, this is the SOA stuff. We can't use is SOA here. I just keep copying and pasting stuff. We can't use is SOA here because this is actually where it hasn't been converted yet. So we're looking for an array with SOA on it. Then we convert it to be a struct. And the length looks like for each member has a type node. Each member is an identifier, which has a type node whose second child is the length. So wait, let me think about that again. So we need to get the member, and each member is the child of the data type. So data type child 0, that will get the member. The type of the member, the second child of the type of the member should be that expression. I think that should get it. It's pointless, however possible, that they could make an SOA from a struct that has no members. And it would be nice if that didn't crash. This is assuming at least one child. Can't be bothered doing that case right now, so let's say handle no members. So we're going to take that and we're going to auto-convert it. I don't think we need to actually auto-convert this one in place. I think we can just do that. Yeah, because we're going to move it into these slices anyway. Where do we, oh no, we're going to put it in the allocator. Okay, yeah, the slices don't actually store length information themselves, but it is in the allocator, so I guess we could get it out of the allocator later, because I think we will need it later. And now we want to change all of the members into slices. So for member in LHS node.datatype. Children. So for all the children, yeah, so for all the members, so that was the first member's data type. We need to change the member data type to basically be like this. Right? Basically it becomes a slice. So it was an array. The member here gets converted to an array, and then that length needs to get replaced with a slice, with a range, and that makes it a slice. That's what I'm trying to say. Okay, so that's that conversion done. So now this is, because we're dynamically allocating, this is going to be actually not a struct of array, but a struct of slices. So down here, in this allocator part, we do need to make sure that the allocator is structured correctly. So I think here we can use as SOA because it's converted now. Oh, we already did use, because we're in assignment, yeah. It was, where was it we couldn't use it? Yeah, left-hand side expression, we couldn't use it. Okay, let's get rid of all these files. So in here, we say if it's an SOA, yeah, if it's an SOA, we basically just do this part, I think. So this is basically setting the argument to the allocator, and we're saying, oh, this is where we use the length. No, but that's what I said before, yeah, that it goes into the allocator. So it's going to be the length of that was specified in here, multiplied by sum literal, and that sum literal is going to be the size of the struct, and that's still valid. Like that's kind of the same as how an array would work, and that's still valid. It doesn't matter that we are arranging the data differently in memory. It's still the same data, still the same size. So I think that's good. Now we need to go to generation. Go to assignment. And yeah, so this is the allocator stuff. So this is where we're processing the actual assembly for an allocator. And this kind of default case, it's kind of, not sure if that's a good idea that it's a default case, but anyway, this default case is for memory allocators. So it allocates a little bit on the stack, which will be the size of the LHS type node. So that would be the size of the stuff that exists on the stack, which is essentially a slice, aka 16 bytes for every member. So this would be, I think, 48 bytes, 3 times 16. So that's the stack portion. That doesn't change. This is where we're grabbing we want to know the length. Well, oh no, it's actually we're getting the size. We're getting the size. So here, if we're dealing with an SOA, I guess an LHS node for that, then actually what we need to do is say size is 0. Then because we have a struct of arrays, we kind of need to extract, or have a struct of slices. We need to extract from each slice, what is it a slice of? And we need to add up all those sizes. So in this case, there are slices of U8s. So for each of these members, we need to find this U8 and the size of it so we can add them together and essentially find what is the size of this struct. So let's say for member in LHS type node.children. And so that member is a slice. So children 0. Wait. If the member is this, yes, a type. So each member of the struct, maybe we go back to this LHS code because it kind of, that was where it gets created. I can't remember how things are structured. Yeah, so each member of the type node is an identifier whose data type is a slice. Right. So that's an identifier whose data type oh my god, it's a slice. So the data type is a slice, and the first child of the slice should be the type of the element. Yeah, member node data type. I'm not sure why, like why wouldn't we just go like this? I feel like that's actually a bit clearer. I hope that doesn't break anything, but like, yeah, we set it to what the type of the node was before. So this is the thing we want to get the size of. So let's say we'll say 2 byte size of that, and we'll add that to the size, and then at the end we should get the full size. So we can set the size to that, but the size is actually, would it be that? Because that's crazy. But this is basically looking, so that the right-hand side node has been changed. I think I need to. All of this like messing with the AST is quite confusing. So the allocator node, yeah, so it's like nested in something. Here it's just a number literal. Oh, I think what I forgot to do was append it. I need to put it on. I actually need to add that allocator node. So by adding it to the children, that essentially becomes the right-hand side. I think that's the idea. So for this one, we just had to, the right-hand side was the allocator node. We just have to get the first child. Was that all we did? We got the second child. Because there was already a child added. Yeah, child already got it up here. So the first child got us this. I mean the second child. So the second child in this case would get us this. So we get the second child of that. So the second child of the second child. So it's kind of similar to this. Except we need to do this as well. And actually we need to do a good old strconv. We need to convert that to a string. Like so. Okay, so I think that's figured out the size correctly. So the amount that we allocate on the heap or wherever we're dynamically allocating should be this size multiplied by the length of the slice. This length. Okay. Right. So far, get rid of that. But so far, what have we done? I just want to recap because this is confusing for me also. We've extracted the length. We have converted all the members to slices. They were arrays. Because it's an SOA, that got converted to arrays. And now because it's dynamically allocated, those arrays get converted to slices. We've done that part. We implemented the allocator. So we should, the allocator should be created with the correct parameters. We sort of inject the size into that now. And then I think the last part, because we now have an array of slices, we need to fill out those slices, basically. Each slice needs to have the pointer and the length in it. Yeah, so let's see if we can figure that out. I guess the length would be the easier one. So yeah, we've allocated. So we figure out the left-hand side. This is where we're going to store our stack object. So that should be a stack address. Then we've got a right-hand side. So we came in, we figure out the expression on the right-hand side. So that's going to invoke the allocator basically and give us back the address that the allocator returned. And normally, because it's just a regular assignment, you know, we just have, well, we created a regular assignment. So we went equals and then we did this allocator stuff. So it's a regular assignment, but we don't want to just copy, because this is an address, a memory address that got dynamically allocated. We don't want to set that to the left-hand side, because the left-hand side is actually holding our struct of slices. So I think, again, we're going to have to do, I guess, LHS node, something special. So let's have an else where we do the copy. So for other things, we just do a copy. For left-hand side, first I want to get the length, really. So I need to figure out where the length is being stored. Well, it's being stored in the allocator, right? We remember that. And type checking, we put the length into the allocator. So that's the right-hand side. This was the number that we just updated up here. That was this number. So if we go to child, oh, this was the first child, the number. So this should have been 0. And if we go child 1, that should get us to here, which is the length. Okay, which we're for some reason cloning. Okay. So this should get us the length expression. So I guess we would generate that expression into register 2. And we'll call that the length location. I sure hope that's right. Do we already have a length location? Oh, no, it's just not used yet. And then, now that we have this length location, I think we can say for member in LHS type node dot children. So this is for every slice in the struct, every member in the struct. We need to copy this to the member. So we also need a raw location, I guess, or well, it's actually the LHS location, which, since it's on the left-hand side, that must be memory location. So we just need to grab that, and we'll call it the slice location. So the first slice is just going to be at LHS location. And the length is the second part of a slice. It's a pointer to the data, then a length. So we actually need to say to the slice location, we offset plus equals address size, to be clear. So we're going past a pointer. And then we want to copy. So I guess we can do just a regular copy, which I think takes a context. What else does it take? From a source to destination. So we're going to go to the slice location. We're going to grab the length and put it there. And we just need to say the type, which is basically just so it knows how much to copy. Yeah, like that. And then we can, well, I guess then after that, we can add the byte size of context.program.identifiers U64. Or do we? Well, we have a length type node. Yeah, there's a U64 type node. So we can just say offset past the size of a length, which is a U64. And that will mean that we get to the start of the next slice. The slice location will be the start of the next slice. So I call it the raw part. This is the part of the slice where we need the pointer, so we need to figure that out. So this, I think we're going to need to do at runtime. The calculation of it, like this length well, this length was also calculated at runtime. It's a little bit inefficient actually, because it was calculated in here also, and now it's being calculated again. So a little bit inefficient, but can be cleaned up later, I think. So if we want to get this this one here, we have to do something a little more involved. We need to know what is the offset in memory to the start of that slice. So again, it will start so that's where we're going to put it. Oh, the right-hand side. The right-hand side was the pointer. That's right. So can we just add an offset to that? No, because that's a compile time thing. I think we need to make a raw location. So the raw location can be if we copy to a register, we copy this to a register, and the register we're going to copy to, because that's definitely a memory address, and we're going to copy it to, again, we need to make sure, you know, like before, that we don't override things. So it looks like we were using register 2 here. Let's change that one to 3, and this one can use register 2. Whoops, and it will need, I call it the reference type node as a type. Okay, it's a pointer type basically. Okay, so now we have this address stored in a register. So I think what we want to do now is we can take that raw location, and we can copy it to slice location. We'll call it reference type node, even though these are, you know, these are both, well, it's type reference, which is also, it's the same size, but for correctness, we call it reference type here. So this is copying that in, and raw location now we need to update. I was going to just put it in here, but we don't actually want to do it every iteration of the loop. Maybe if we skip it the first time and just do it on subsequent times, subsequent iterations of the loop. So if index is greater than 0, then we need to update this raw location. So that's going to be we're going to need to take that raw location. We're going to need to have, well, we're going to need to calculate the size of the member times the length, which we know is here. So we need to get the size of the member, multiply it by this length, and then we know the offset. So then we need to add that to raw location. Okay. So I'm going to call that member offset location, and that's just register so we'll make that register 2, 3, 4. So we're using a lot of registers here. Hopefully that's all right. Does this length location, you know what, this length location, it might end up in a register. It's not, yeah, it might. I don't think it will, but anyway, that's okay. So this member offset location, first we want to, do we have any examples of writing assembly? Here we go. Okay, so we want to move. So I guess move is generally, it's a copy. I use copy to do moves. So we want to move into the member offset location the size of the member. And the size of the member is this, right? So let's say member size. And we'll just make an immediate of it. So there's a hard-coded value in assembly, and we'll copy that into the member offset location, into this register. Now we want to multiply. I don't have an easy function for doing that, so we will just write the assembly for that. So that will be multiply. We're talking about unsigned stuff here, so just use. Oh, so actually multiply is potentially more complicated. I should check. If we go to generation of an expression of an integer and multiply. See, this is, see, this uses a whole different thing. But then I'm actually not sure why we did it this way, because I was looking at this stuff before. And was it here? No, here, yeah. If I look at mul, so there's imul, which is of, oh, so that's the DAX one. So that's this one. Look, there's this imul, which is just like a standalone thing. So is that, yeah, so this mul looks the same. And now there's an imul, which is like register and those two. Register, oh no, that's three. That's three things. Okay, maybe I shouldn't get too cheeky. Well, this one is just register and then register on memory. So is there a mul like that? That's the one that I'm using, I guess. That's the imul I'm using. For some reason, I remember having the idea that there was also something like that. So imul has that form. Mul also has that form. But imul has these other forms. And mul does not. Widening unsigned. Yeah, that's the three parameter. Okay. So we would either have to do the complicated one, I guess. I don't know, I'm gonna try just doing mul like this. Because I was playing before and I'm sure I was able to do that. Multiply by element size, let's say multiply by member size. No, it is the member size, so multiply by length. We don't need a precision. So we want to multiply this member offset location by the length. So let's get the length location, like so. Okay, so we multiply it by the length. That gives us the offset, and then we want to add that to our raw location, right? So add to raw offset, we'll say. So, oh my God. So we do an add of the member offset location to the raw location, and that's what we put into the slice. Okay. I think that's right. So I think that's going to set all that information correctly for both, for all members. And that's basically what we want. I think that's it. So if I run this, it doesn't crash, which is nice. We don't get any assembly errors. We didn't get any assembly errors, even though, well, let's see if this multiply actually works though. Yeah, because that other multiply prefix multiply left. So that's putting something into racks and taking it out of racks. Oh, interesting that it has this prefix, which is, yeah, so it's dealing like with whether it's signed or not, even though if it's signed we just do this. Now this is all a bit confusing. So this might not work properly actually, just doing it by itself. If we just do that, it might be expecting. So this is the result, the right hand side. Oh no, this is operation size. So this is a size in a thing. Ah. Because I guess that thing, that non-immediate location, that could be a memory address, which is why you need the size. So if this works with two operands, not a size in one so this is just actually one operand. So if it works with two operands, the assembly didn't complain, so I guess it's okay. I accidentally closed that just now. Then maybe that's fine, actually. I can do an assertion. Debug assert. That means we need, oops. Oh my God, did it again. OS debug. Oh, debug goes there. Yeah. But whether that's actually accessing it right, maybe we'll have a quick look at we're just under an hour now, so if this is actually working properly, which it seems to be, but I mean, this assertion is just testing, like, the 9 got put, oh my God, what is going on? The 9 got put somewhere, and this assertion is just kind of asserting that it did actually get put there. But it's not really asserting that it got put in the right place in memory. So we don't have our, that's right, one thing I wanted to do is in these configurations is add intermediaries. We'll do it here as well, and does that take the intermediaries flag? I'm not sure. But if I run that now, yeah, now we have the NASM file. So if we can look at the main, this is not actually a statement. So then we should get declaration of 5. Yep, so we allocate 4 bytes, we put a 5 into it. This line here is the creation, so that's going to be a big one. Yeah. So we do some allocations. This is our auto conversion of this length, because is implicitly an I32, so we convert it to a U32. I think that should be a no-op. But I think that's what's going on there. We're doing a multiply, so we multiply the R. Oh, it looks like it's just moving it into a register maybe, and then I don't know. And because now it's saying R13, not R13D. So we're multiplying by 3. And putting that in the heap. So this is, so the heap call, yeah. So we're saying 3 times some memory address, and that memory address, I assume, will be this length. So this thing that got allocated here. So plus 68, yeah, this is, we just allocated 68 bytes, so plus 68 will take us back to here. Yeah, so it's 5 times 3, so it's the size of the thing to allocate. That's right. Great. We'll just ignore this allocation deallocation business. But I guess R12 is now, well, I guess we can't ignore it. We deallocated 8 of the 68. Then we moved to the top of the stack to R12. So maybe this is, I guess this is the return value of the heap. Must be. We deallocated a bit more. So now we're copying R12, which was the thing we got returned. We're copying that address into R14. We treated it like a memory address. That's interesting. I guess it is. But is this saying like the value that was in that? I don't know, I get a bit confused by these things sometimes. Then plus 48 is that the return value? Here's our loop. Here's our loop. Ah, right, see, look. So R15 plus 48. Ah, so this R15D is actually, why D? It's 32-bit, isn't it? Because that's grabbing, well, that's interesting. It's a conversion. Converting it to 32-bit. It's because isn't it grabbing the address? Or R15. What's the lowest? There is an R11 in here, right? I think R11 is the lowest. It doesn't actually use R11 in here. We can definitely see, you know, like it's copying to RSP plus 8. Which I think is still, you can think of it as part of this allocation. So I think that you can think of it as something on the right-hand side. And then I guess I thought we were going to copy it to the left-hand side at the end, but I don't actually see that happening. So maybe that copy is still needed. You know, we removed that copy. If we go to here, wasn't it here? And I don't see a removal of a copy here, so that's what makes me a bit confused if that's it. Oh no, here it is. Yeah. So this was the initial, the copy of the right-hand side to the left-hand side. But we're using the left-hand side directly, right? Slice location. We just keep offsetting it some more. But I feel like it's starting. So it seems to be starting just at RSP, this slice location. We've already done this when we grab it. If that made any allocations, they should be undone. I think they were undone. I think this, it gets a bit confusing with all those allocation deallocations, but I think this here basically corresponds to this line. So this 48 by, yeah, remember I said it was 48, 3 times 16. So I think this is the left-hand side allocation. And because we've deallocated all that, RSP is now pointing at this, which is our new SOA, or SOS, structured slices. So this is right. RSP, we go to RSP and RSP plus 8, and we copy in R14, which is holding our return value. I'm still not sure about this square brackets part. The copy to register. I think it's returned. Yeah, that part I'm a little bit unsure about whether that's correct or whether it's like, I'm kind of thinking it should be just like that. But let's leave that for now. Let's just assume that's correct. So this is the pointer to the first slice. Yeah, the slice for the first member. This R15 should be the length. RSP plus 48 goes back to here, which is a 32-bit length. It's this. Yes, okay, it's all starting to make sense. So this is the 32-bit length, that's why it's R15D. When we put it as a length in the slice, it's 64-bit, that's why it's R15, not R15D. That's an implicit conversion you can do. So that's handling the first slice. Then we say, okay, R13, I assume this must be the size of the first member multiplied by the length. Yes, that's the length. Then we add that to R14 and we get our new pointer, which we put at new offsets. This always stays the same. The length is just the same for all of them. Then again, we do more offsetting. Okay, I'm very happy with this. It took me a while to reading assembly is not easy. And I would like to clean this up a lot. I would like to really reduce the amount of allocation deallocation business going on. There's a lot of superfluous copies that happen. This one, for example, only happens because there are all these allocations, deallocations. I want to make sure I don't lose track of stuff. So we could potentially, remove this one, these two, these 3 lines. Yeah, we could do some simplification for sure. And now this assignment is this one. So this is the part, oh my god, again, this is the part where I figure out the memory offset for this here. So it's SOA.A. So A is the first slice. So it should be the memory address of this SOA, basically. But then it's the third one. So it should be basically just +3 to get to it. It's the third A, so it should be +3. So if we get +8, yeah, so this is bounds checking basically. So RSP +8 is getting the length of the slice, slice A. Remember, this is like that now. Effectively, it's been changed to be like that. So we have a struct of slices. So slice A is at the front of the struct, and so the length is at +8. So this should be the length. Then we get a 3. So the length multiplied by 3. Oh no, compared to 3. To make sure that's not out of bounds. Then we get the pointer to the slice, and at pointer +3 is where we copy it. So this is just bounds checking. This is the actual operation. We get the pointer to the first slice, and we go +3. So this would be RSP +16 if we were to go to the second slice. So if I change this to B, then this should become RSP +16. Boom. And this is RSP +24 because we're getting the length of that slice instead, even though the lengths are all the same. Everything else stayed the same. And this offset here should change when I change this. So if I change that to 2, that should change to 2. Yes, and we're bounds checking against the 2. Perfect. Okay. Oh, assertion failed, blah. Ah, right, because we were checking with 2. Oh, oh no, because also it's B. Okay. Right. So, I hope that kind of run through of the assembly made sense. It's not something I do too often, but we are going to dig a bit more into assembly in some of the sessions coming up. Like I say, I want to do some improvements and reduce some duplication of some assembly generation, so we need to verify that. Yeah, but I'm pretty happy with this. So thanks for stopping by. Have a good one. Ciao for now.